Thank you very much. Funny enough, I started my career at BGS in early 70s. In those days, it wasn't BGS. It was called Institute of Geological Sciences. And we were mobile staff. You had to move whenever you were asked to. So I was seconded to the Campbell School of Mines first for the Hot Rocks project, and then to the European project. So I've been with the geothermal for nearly over 40 years. My presentation is in two parts. First, to explain the evolution of how geothermal has moved forward, and the second one is if we can use geothermal to address or mitigate climate change issue. As you can see from the slide, the geothermal can be roughly split into two, conventional and unconventional. Let's see if I can get. The hydrothermal, conventional hydrothermal is in areas like where the crust is thin, or a caldera, various other places where there's natural fluid and the crust is relatively thin. But you find that these areas are fairly limited, like in New Zealand, west side of US, California, Italy, and Iceland. But that, I'll show you later on, when you match supply and demand of energy, that is a real poor supply of energy. So one had to come up with a new idea. And an unconventional came in sort of early 70s. Los Alamos scientists working on nuclear bombs thought, well, why can't we use existing granite to create a permeability in it, and so we can extract heat? So they came with an idea in the 70s. Similar project started in Cornwall, and we worked together on this. But this was a sort of a relatively closed system. You take a rock mass, particularly like granite, with a fractured, you stimulate it, enhance the permeability, and the idea is that you circulate fluid in there, and the separation was around about 800, 600, 800. That gave you a life of 25 to 30 years. So a number of projects started. These are only a few, but 12 different projects started. But one of the problems in that is that, one, the issue of seismicity, which everybody is concerned, and to create a permeability that is sufficiently low to be able to extract heat, but not use a large amount of generated energy back into the pumping. So while we were developing this, this third project started, which is here, Sulz project, which was actually based very similar. This was Sulz project was a European project. Britain, Germany, and France combined together, and the EC persuaded us to give up the national project and concentrate on one, because we wanted to go to 5,000 meter deep and create structures like very much on that side, create a permeability. And this, while we were working, we almost came across existing open faults. Now, we did see these faults in Cornwall as well, but we tried to avoid that, but we thought that these faults will steal water away. You want a closed system where it can circulate. But eventually dawned on us, why don't we use a natural system? That existing faults are natural faults. Let me just see. So a number of, this has been so successful, tapping into a natural system in igneous rock at 5,000 meters or deeper. So the first system commercial was produced in Landau in Germany, funded by Pfalzwerke. It was successful. The reason we went there, because the Landau and Strasbourg is a very old oil field, and they had a seismic record reflection. So we were able to process it, find two faults, and intersect it, and that was a successful project. This was a like hydrothermal system in igneous basement. So once you're successful, people come and say, you're lucky. You'll never be able to repeat again. So 9 kilometers away, another project was created, Insheim. That was also successful. I'll be repeating some of these. And third, further south, so Strasbourg, another one. And now we're trying to create a similar system at the Eden project in Cornwall. What I'm saying is that it has evolved from hot dry rock, which was a closed system. Now we're going to an open system, and we're trying to use a natural fault. This is a summary diagram. Originally, we started here. This is permeability. High permeability, low permeability. Originally, hydrothermal system relied on very high permeability system like Desert Peak, Geyser, and so forth. Then we jumped from there straight to here, very low permeability. But during the investigation and circulating this, we found there was an alternative, which means there are faults, deep faults. So now this is a favorite. Using existing fault system, you don't have to do a lot stimulation or anything, and you get, I'll show you. This is what I'm talking about, the Sulz project. We found presence of large fault depth, and funny enough, when we injected, we were able to, there were seismic boreholes 15 to 2 kilometers away. We were injecting, we see pressure response that far away. It gave us more and more confidence that these faults were big. These faults can carry hydraulic conductivity, produce fluid infinitum. One of the concerns was that if you produce a certain amount, the pressure will drop in the fluid. But the experience shows that they recharge themselves. Again, as mentioned, one of the concerns with conventional hot dry rock is when you inject to create reservoir, create seismicity, and it is concerned. That is not the case in a natural system. And one of the key parameters, there are faults in that. One of the key parameters, these faults, we found they have to be aligned in maxima in situ stress direction. And the idea there is that you've got less confining forces on it, they're more likely to be open and carry fluid. Now, I'll give you an example of this fault. This is from Sulz. This is depth. And this is a flow log. In other words, you measure with a spinner where the fluid is leaving, at what depth. And you can see here, 10% of the fluid, you can see here, 10% of the fluid leaving just below the casing shoe, where there is a fault. 70% is leaving at depth 4750, 70% through a fault, natural fault, which is 1 meter wide. And you can see this is what they call UBI. It's an image of the borehole. And normally, when you borehole intersects, or the fault intersects a borehole, you get like a sine wave. And this is highly fractured. That's 1 meter, highly fractured. So 70% is going through a natural system, and similarly, we found another 20%. Originally, you would have thought joints like that, when you inject, fluid will go through it. But it became more and more apparent the natural system is overriding what we're trying to do. So that gave us an idea. Perhaps we ought to look at the natural system. This is a second project, Inside. So what we've done there, we found one fault, and there are two concepts. Original one in Landa, we found this fault through seismic reflection, drilled into it, you go orthogonal and start production. And when the water is cool, you go to the adjacent fault, and we used to inject it. But that is not necessary. What we found, that one fault, you get a single fault like that. If you have a production well here, an injection well somewhere around 700 to 800 meters apart, that is sufficient. Tracer test has shown that the tracer returns after 2.5, 3 months. So your cold water, when it goes down, because of density contrast, it goes hurtling down to the bottom of the fault, very, very deep faults. And they come back after 2 to 3 months. So that, and it's also recharge. So it's amazingly permeable. It's like having a hydrothermal system and igneous basement. As I said, originally people thought, oh, you're lucky and so forth. And now there are 5 commercial projects working in France and Germany. And the output, as you can see, this particular one, it produces up to 80 liters per second, continuous. We produce about 5 megawatt, which can heat about 8,000 homes. And thermal hours is 10 megawatt. Again, we're going to heating them. So you've got perhaps we need to change our concept. Our concept at present is we have a big power station, we transmit everywhere. Maybe we need to integrate local power station with the local community. So this small-scale production is friendly with the environment, is linked to the local population, and it doesn't need to transmit over long distances. So maybe perhaps we ought to be thinking slightly different our concept how we live. And we want to get this similar thing at the Eden. And this is a satellite image. And stress, maximum stress is something like this. You can see lots of faults, right? The Eden project is here near St. Austell. So that's what we try to get one of these to demonstrate it. Now, this here is an expression of that fault to the surface. This is over 1 meter wide, just to show these fault at depth are not small, they are huge. And I was talking to a gentleman called Aki in Japan at one of the conferences. Aki used to be a professor at MIT, and he tried to predict earthquakes. And I think you will see anybody who does seismic, it's quantitative seismology by Aki and Richards. And he perhaps indicated that people think crust is a single entity. He says rubbish. Crust has lots of stress relief mechanism in it. And this could be a part of a stress relief mechanism. So if we can exploit here one fault, which is, one hopes a depth will be something like that, then there are lots of other faults within here. And number of studies have done from Imperial College to CSM ourselves to Atkins, they all come with a similar figure. 20% of electricity, UK's electricity, can be supplied from Cornwall and Devon. Yeah. Yet, this study has been donkeys years ago, yet there has not been a sufficient initiative to look at it until recently. You wonder, can you really carry that much fluid underground? This is an example. Large amount of flow. We talk about 70 liters per second, but you can be 100 or 150. This is a Willjane mine in Cornwall. They had to pump 60,000 cubic meters a day. That is equivalent to 700 liters per second. So this is another demonstration. There is a huge quantity of fluid in igneous basement. To a lot of people, this may be a surprise, that granite in principle is supposed to be tight and things. It's not the case. We're seeing again and again there are big fault systems, and we need to exploit this. That's go back. That's where we are. Eden project originally was a China clay pit, and we were able to see this 30 miles away from Rosmanos near Penryn. That's been converted to Eden project. And I selected the site because one of the things is when you convert electricity, a huge amount of heat is still left. And perhaps we can use that to heat the biomes, and that will reduce the use of generation of CO2. And the other advantage would be something like 2 million visitors come every year. It's a very good way of educating public. That's the way forward. That's the first part, to show how the geothermal is evolving. Now, how can we use this to address the climate change? There was a meeting in 2005. We were writing a report for the IGA to persuade government to take on geothermal seriously. And the meeting was at Washington, D.C. And it became clear that if geothermal, which is the biggest source of energy, is going to help climate change, we have to match supply and demand. Yeah. What is happening, the demand is in one place, and geothermal supply, particularly if you use hydrothermal, is another place, and you can't seem to blend it. What frightened me, and I think perhaps this is what made me concentrate more on the climate change. The forward modeling by the World Bank shows that by 2050, the model shows the equator will be 55 to 60 degrees. And the outcome of that is going to be horrendous. Expected starvation and human catastrophe, because they will not be able to grow anything. They have no option but to migrate to northern and southern hemisphere. And he even startled me when he thought of hundreds of millions have to migrate. They have no option. They have to move or die. And I can see what you see at present, people coming in, we complain about it. This is a huge catastrophe waiting to happen. Unless we do something, as he suggested, there will be wars. And so this has to be addressed whether we like it or not. So issues it's obviously conventional geothermal is not in sync with where the demand is. But if you use unconventional, which I was explaining, that will provide heat, power, but we're also finding it at like Insyme, there's those in the filters, there was a white material trap. We found that to produce something like 0.5 ton of lithium derivatives. So not just the old circulating brine in igneous basement, provide heat and power, minerals as well, and also indirectly reduce CO2. So it's a win-win situation if you go in this direction. Now, sorry, I better hurry. This is taken a map of, this is a density map of human, this is over 1,000. So this is where the energy need is. India, China, Western Europe, and eastern side of US. This is supply of hydrothermal. You can see here. Where is it going? All that sort of area. This is not in sync with the demand. So obviously hydrothermal is not the way forward. We did an assessment. Hydrothermal provides, this is equal to 2.1 terawatt electric was 1 year's supply. So hydrothermal contributes very small. Non-electric has got reasonable. For the unconventional EGS, if we move forward, that is the one that may help us to address the climate change. I just repeated that. Now, how do we move forward? This is a very important slide. It has to be an international effort on mapping. So my trying to put together with IGN thing is we international get together and map these deep faults on all the continents and all the countries first. We can help characterize the faults. In other words, faults with the deep fluids in it is the one that we want to exploit. Improve economics. Now, drilling is the major cost in accessing this. Currently, we've found that percussion drilling can drill, even in igneous rock, 20 meters an hour, which reduces the cost dramatically. Yeah? Now, what we found here, like at Sulz, there was a point of focus. At Sulz, we had scientists and engineers from all over the world working that they allowed him or gave them an opportunity to understand and take back the information back to countries. Again, international cooperation helped generation new ideas. I think we also need to create some sort of international center of excellence. Because we have got limited time, we need to get this message across to all the country. Funding mechanism is a bit difficult one, but I'm sure with the World Bank, that the first project in the particular site or particular country can be supported by the World Bank. Once we demonstrate that it works, we hope that the countries will themselves take over. Encourage direct heat use and develop mechanisms scaling up to. There was at Sulz thinking of going up to 100 megawatt. We didn't do it. I've done a paper on it, and it's available how we can do it. And we need to have mechanisms to encourage population areas of the world to take up EGS. I think this is one of the key players in mitigation of climate change. Thank you.
Thank you. Thank you for that excellent introduction. And plead for more. Questions from the audience?
Spence, British Geological Survey. What kind of cooperation in terms of the provision of drilling technologies, you know, the widespread capability to reach the required depths quickly, you know, and not have, you know, try and share that risk of the drilling operation. What kind of solutions can you foresee to address that?
We did that under the IEA. When other countries wanted to, they used to come at source, like the present project in Cornwall continuing. That is a team, same from source. So we make sure that the know-how can be transferred. We try and provide the same team, and they can train their team. International cooperation is important.
Hi there, it's Kim Dowsett from the Environment Agency. You mentioned some of those schemes in Germany were successful.
Yes.
Does that mean they were, I'm just thinking in terms of how, were they commercially viable, were they making money? Because obviously that's what investors and people putting money into these schemes want to know in order to do one in the first place.
They're both commercial scheme and they're making money, particularly now with the lithium coming up. It'll even enhance more sort of economic involvement. There are two schemes in the south, which is in northern France. The Ritterhofen project is quite cleverly done. They don't necessarily convert heat to electricity. They transmit heat 20 kilometers away with 1 degree loss on temperature, and whole pharmaceutical industry is built around it. So it's not necessarily to convert electricity. Like Jörg in Landau used to process various other things, help farmer dry their crop, and a whole range of things you can do. So heat itself is so valuable that you may not necessarily have to convert electricity.
Nick Shaw, Leeds University. Thank you, Roy. That was a good talk. I think it's also worth mentioning those German projects benefited from a risk coverage. So to help them go through the pilot, they had a risk premium provided by the German government in much the same way as the Dutch government provide an SDE environmental coverage to cover the exploration risk. If it's below a certain level, the government will pay for the well. And I think that's an area that would be of great help in Britain to besides the legislation, give also risk coverage for exploration.
Yeah, I agree with you. I have very high regard for German government. I worked with them through the IEA and so forth. If you have an idea or anything, they'll help you to take it up and move forward. The Sulz project for first 3 years was run by the staff from Cornwall. Yeah. We were supposed to go 5 kilometers deep. It never transpired. All the idea, everything had just disappeared. It's a shame, as I said, various studies shown 20% of electricity can be provided, and we haven't done anything for the last 35 years.
Frances Wall, so Camborne School of Mines, University of Exeter. So you gave two figures there which seem to lead to slightly or different visions. One was your one that Cornwall and Devon could provide 20% of the electricity, this huge figure. And then earlier, though, you'd mentioned the idea about having local power stations all linked into the community, which I guess would be heat and power. And I wonder what you think the vision might be out of that. What's the most realistic thing that we should be aiming for with geothermal?
I think you should use geothermal in every form. It doesn't have to convert to electricity. There are lots of aquifers in Midland and other places. I've been trying to encourage them to use it, but there is no government support on this one to move it forward. There is other misunderstanding about Scotland as well. I was talking to a lady from Statoil through IEA, and Scotland is completely disregarded because the ice age has cooled the first 100 or 200 meters. But the lady she said that Statoil have found that when you go around 5 kilometers, the temperature is similar to what you would expect in other places. So Scotland is underestimated in terms of resource. So my colleague we tried to persuade the Scottish government to put three 500-metre deep borehole in strategic position to re-evaluate the total Scottish resource, but nothing took place.
A good challenge for us. I think we should wrap up the discussion, but I like you finishing with this point of multiple use of the geothermal
Yes.
resource. Because I actually visited the geothermal plants in Iceland recently, and what impressed me is they're using it for heat, power, pharmaceuticals,
Yeah.
health products, hot water for the district community. It was a very multi-use geothermal.
But look at Paris. Paris is heated, I think equivalent to 2 gigawatt by small boreholes. Because the same aquifer system comes to Britain, and we're not using it.
I think you leave us with a good challenge and a vision. so-
You can attack it. Heating is the perhaps the largest user for energy. Why don't we use natural system to do it? And government should pay for the heating network. When Landau was installed, the German government said, right, we'll pay for the heating network.
Right, I think we'll wrap up there, but a good point to finish on. Thanks very much. Right. And you nicely introduced Germany. So our next